Okay, so this is going to be for one of your first assignments. It's going to be a homework. It's going to be primarily focused around pressure and how to solve for that, the sum of forces, things like that, but also a couple of other things that are going to be on that first homework. So be sure to take good notes, watch it a couple of times, and then definitely use this when you go to solve for your first homework, because everything that we're doing on there will be done in this video, aside from specific examples of temperature going from Celsius to Fahrenheit, things like that, since I have already done that in the refresher video. So if you haven't watched that, be sure to go and watch that as well, or even stop here, go watch that first, and then come back. Okay, so these are some things that you'll just need to know. P denotes pressure, which is force per unit area. T is temperature. And then density, which looks kind of like an E, but not an E, is mass over volume. And this is pronounced rho. And then lowercase v is specific volume. And that is volume over mass, which is the inverse of density. Okay, and then of course uppercase M is mass, and then uppercase E is energy, and then lowercase e is specific energy. H, enthalpy. And what's some more? Okay, we've got E, which is internal energy. H, heat. And then S is entropy. Okay, so just those are some good ones to know, that when we start using our formulas, you'll see these in there. So let's get into just some of the formulas. Okay, so the ones that we're going to be looking at today is density, and then that's mass per unit volume. In SI, that will be meters cubed, and then kilograms. If this was EE, this would be pound, okay? But this is in SI units, we're just going to use that again. Wow. And one thing to do is always go back to the primary units. So always return to primary units. For example, if you're given grams, bring it to kilograms for this. If you're given, you know, whatever, these are your primary units. So you want to return to these. So when I say always return to primary units, I mean what's in your formula. And then your specific volume. Which is the inverse of density. V equals 1 over, whoop. Okay, and this is in SI again, meters cubed over kilograms. And we will do an example of this right now. Let's do a specific volume since we're talking about it. Okay. So for specific volume, let's do this on a mass and mole basis because your homework asks for that. So what we're given is 25 kilograms of O2 is contained in a 375 liter tank. Okay, we need to find specific volume, mass, and mole basis. And here is our solution. Okay, so we know that specific volume is that over total volume over mass. So right here, we're given 375, which is our volume. And then this is our mass. So that's mass, and that's our volume. But they're not in homogeneous units, right? So we've got liters here, and we've got kilograms here. And this, we know, needs to be in meters cubed over, ooh, my pen is kilograms. Okay, so this is good. Our denominator's in the right unit, so we just need to get this to meters cubed. So we are going to have 375 times our multiplier, 10 to the negative 3 meters cubed to get that liters into meters cubed over 25 kilograms. Okay, I zoomed it out a little bit, see if that helps. Okay, so then that gives us 0.015 meters cubed over kilograms. So that's our mass basis. Okay, I'm boxing in my solution so that I know what it is. Okay, now let's do the mole basis. Okay, so on here, this is going to be denoted with a line above. So right here, you've got just the V for the specific volume. Right now, you just put a line over it. And then you're going to do your M times your V equals, and this is going to be a constant that you're going to have to find from table from table A1. And remember when I said that you have a bunch of tables in the back and that I will give them to you electronically? I'm going to use them electronically when I am showing you how to solve these things, but when I'm working them beforehand to make sure that I have all of the figures correct, I use the paper version in the books also because it is a lot easier. So right here, here's all of your units. Right now, we're solving for mole. So here's the molecular weights, table A1. So we're going to go down to table A1. Right here, we need this constant. See, we're looking for M. You see that it's in kilograms or kilomoles. And then here's oxygen, which is 32. So 32 is our M. See that? 32 is the M. Okay, so we're going to take that and we are going to put it in 32 kilograms over kilomoles, because they gave us these units in the table. And then we're going to multiply that by our V that we just solved for, right? So 0.015 meters cubed over kilograms. And then this is that of O2, because that's what was given right here, equals 3.82 meters cubed kilomole. Okay, and this is, see, we've denoted mole, but we'll do mole basis. Okay. And I'll write down this. So this was from table A1, and it is O2 equals 32 grams kilomole. So really easy, but it's just good to work through. And there's one of these on a homework for you to work independently. Okay. So that is our specific volume example. And let's move on to pressure. So this, you will see this a lot throughout this semester and next. That's why this is done up front. And so, there you go. Well, I can't seem to, is it on the screen? No, I'll just, okay, there it is. Okay, so we've got pressure. And that's the force per unit area. Right here. Okay. And this is in newtons, again, SI units. That is in meters squared. So right here. Or pascals, right? Okay, and so one thing to note about pressure is always normal to, right? Right here, so it's always normal to. And that will make more sense if that's confusing when we work the next problem. You have two different types of pressure. You have gauge pressure, which is pressure absolute or system pressure minus atmospheric pressure. And then this is system pressure is greater than atmospheric pressure. Okay, so that's one type. And then the other type is vacuum pressure. And that is just the opposite. It's when your atmospheric pressure is greater than your absolute pressure. And again, this is your system pressure. So this is your oh. Okay. And then what do we mean by this system pressure, right? So these are your two types, but then also just to note that your system pressure is your gauge plus atmosphere. So just something to note on here. Okay. So let's work a problem. Yeah, let's do an example. I guess it didn't want me to erase it. I would normally scan and upload these, but because they're recorded, I know that you guys can always go back for anything that I'm writing. But if there is an instance where you guys want me to start saving these and then uploading them after with the lecture, I can certainly do that. But I know that you guys can go back and look at them, especially because these are going to be pretty short-ish lectures compared to in an entire class. Okay, so if we have a piston cylinder right here, and then this is our piston right here. It's that. And we've got the pressure of gas and the pressure of the atmosphere. And what we know, known values. We know the atmospheric pressure. We know the area of the piston. And we know the gas pressure. And we need to find the mass of the piston. Okay? And so when we talk about normal 2, I'm talking about like this is a y-axis and then this is an x-axis. And so when I talk about normal 2, we're talking about in the y direction, right? So when I said, hey, pressure is normal 2, well, that's not very straight. Let me see if I can get this to erase. When I'm talking about if something is normal 2, that's what I'm talking about. So I'm talking about this being in the y direction, and if the pressure was coming in from the sides, then that would be pressure coming in on the x-axis. So when I denote y like this, that means normal 2. Okay? And so what is this piston doing here? So we've got the pressure of gas going up. Okay, we've got that pushing up. We've got the atmospheric pressure pushing down. What other pressures do we have? Well, we have the weight of the piston right here, right? Because that's a solid. So we've got, and that's pushing down, you know, so all of this is pushing down, all this weight. Okay, so how do we solve to get the mass of the piston? Well, if you remember, we can use the sum of forces. And see this y right here, that's the sum of the forces in the y direction, so either negative or positive. And then we can use this to find a system in equilibrium. And what does that mean? So that means that all of the forces pushing down must equal the forces pushing up, right? So this is not moving. All of these are stagnant. They're just, it's in equilibrium. It's not going up, it's not going down, it's just in equilibrium. So everything must equal. So let's draw this out just to isolate our forces and kind of see how they're going either negatively or positively. So you've got the atmospheric force, okay? And then you've got this piston right here, and that's the weight of the piston. It's going down. And then within this, you've got the force of the gas. Okay, and so we can write this out into these. So you just sum them up. So if the force, the atmospheric force, is going down, well, then we know that that's negative, right? So it's going down, it's going negative on the y-axis. So we're going to do negative the force of the atmospheric pressure, and then negative of the weight, and then positive of the gas because it's going up. Equals 0. Okay, and so we know from before that pressure equals force over area. Okay, and then we can rewrite that as force equals pressure times area. So we can rewrite these to get to this mass, or to include this mass in here. And so what we'll do is we'll take this force right here, see, because force equals pressure times area, and that will go negative atmospheric pressure times the area of the piston, right? See, because pressure and area times each other equals force, so that's what we're doing. And then we're just going to deduct the weight of the piston. Okay? And then what do we know for that? Well, we know that we have gravity, and that's a constant that will always be given to you. So we're going to multiply that by gravity because that's the force that is drawn this down. Okay? And then we can add, because we're going back up now, we're doing the pressure of the gas, and then times the area of the piston again, all to equal 0. And then how can we find these areas? You know, so what is the area? So we know that the cross-sectional area of a piston is a circle. So if you cut this in half and you have a piston, right? So it's going to be a circle, and we do have a formula for that. So the area of a piston equals pi r squared, or pi diameter squared over 4, just depending on which one you're given, whether you're given the radius or the diameter. And so then we can plug that in and isolate the mass of the piston to one side to get this formula. Okay, so this is an example without actually using figures to get to your formula, so that if you were given because it says right here that we know the values of the atmospheric pressure, the area of the piston, which right here we can take that area of the piston and use whether it's given as the diameter or the radius, we can find the figure for that, and then the pressure for the gas. And then from that, we can just plug into here and get all of the masses. And then plug into here and get all of the masses. Okay, so let's work a problem where we're actually putting all of that into play, but we're also including a rod. Okay, so pistons can look I mean, they're pretty much the same, but sometimes you'll get an example that has a rod. Okay. Let's do it like that. Okay. Okay, so this is your rod, and this is your piston. And again, this is normal to view, and this is gas, and this is the atmospheric pressure, and this is the weight of the piston. Okay, and so what are our known values? So we know that the diameter of the cylinder is 0.01 meters. The mass is 25 kilograms. The diameter of the rod is 0.01 meters. The atmospheric pressure is 101 kilopascals. And then the gas pressure is 250 kilopascals. Okay, and we are looking for, sorry, my pen is lagging. Okay. Looking for, oh, come on. Oh, I guess this is going to be a thing. Oh my gosh. Okay. We're looking for the force of the rod. Okay. So that's what we're looking for. So step one, we're going to do the same thing that we just did. We're going to do the sum of the forces. Okay. And so again, what do we know? We know that the atmospheric pressure is going down. We know that the force of the rod, let's see if I can write this up here. Yep. Rod, okay. We know that the weight of the piston is going down. And we know that, well, I don't know why this is, oh, I guess because it's, okay. Too close to that little thing. Good night. I'm having a lot of glitches on this. I might have to figure out some other way to get you guys these. Okay, and so we know that the gas is pushing up, and we know that we can do the sum of forces to equal, so all of the forces going up must equal all of the forces going down. So what do we have? We have the atmospheric force going down. We have the weight of the piston going down. We have the force from the rod going down. And we have the force of the gas going up. Okay? And again, we're going to use P equals force over area, because we're trying to get here so that we can plug in our known values. We can rewrite that as force equals pressure times area, because we have the forces. That's what our formula is telling us. But what we're given is the pressures, so we're going to use this so that we can use our usable data to plug into our given formula. Okay, and so one thing that's different here is you have to look at actually where your forces are being applied on this. So you think, oh, well, my atmospheric force is being applied all over. Well, is it? So you've got an aerial view. Remember when I said that cross-sectional area of the piston is a circle? This is an aerial view showing you this. Okay, so this is a cylinder right here, and this is the rod. Okay, and then where is this atmospheric pressure being applied? It's being applied all around here. So if you took this formula and you said that it is done all on the cylinder, that would be incorrect because you have a force from the rod as well. So your atmospheric force is actually along the cylinder minus the rod. Okay, so we are, let's see, what is, it's everywhere except the rod, which translates to that's the area that this atmospheric force is being applied to. Does that make sense? I think so. Okay, but we'll plug it in here too. And so, therefore, here's our formula. Because remember before when we took this out and we took our atmospheric force and then we broke that down into our pressure times area, we're going to do that again, but we're going to include this because this is our area. So we have, and we're looking for F rod, so let's go ahead and isolate that to one side. So we've got, let's do P gas first, okay, times the area of the piston, and then minus, because the atmospheric pressure is going down, see, so we're applying it down. Whoops. Okay, times, what is our area? Where is that atmospheric pressure being applied to? It's being applied to the entire cylinder minus the rod. So right here, the area of the piston minus the area of the rod. Okay, and then we've got the mass of the piston times our constant, which is gravity. Okay, and so now that we have all of this, we need to also find what this area of the piston is and what the area of the rod is, because we are given diameters, but we don't know what that means in regard to the area, but we know that we can find it. So before I remove all of that, all of this, let's find those. Okay, so we need to find the area of the piston and the area of the rod. And we have those formulas. Remember, we were just given those dependent on whether or not you're given the diameter or the radius. So the area of the piston equals pi diameter squared of the piston over 4, which is pi 0.1 meters, because this is a given, squared over 4, and then that is 0.0079 meters squared. So that's this one, and then we're going to do the rod. Okay, and then that is same formula because we're given the diameter. And then this is the given, you see up here, diameter of the rod right here, over 4, which equals 479 meters squared. Ooh, okay. All right, so I'm going to erase this to keep going, but All I'm going to do between here and the next page that I write is take all of these known values, so the things that we just solved right here, everything that was given, and I'm going to plug it into this formula right here. So we're doing the same thing that we did before, but whereas we stopped where we got this formula because we didn't, we knew what our known values were, but we didn't have those values. Now we're taking that next step and we're plugging them in. And remember, guys, to be taking good notes so that if you need to go back and refer to them, I'm also working off of my notes because there's no way that I could show the extent of all of these problems on one screen. Okay, so we just found out this formula, right? We just worked that out. Gas times the area of the piston minus atmospheric pressure times the area of the piston minus the area of the rod minus mass of the piston times our constant gravity. This is always constant and it will always be given. It's never changing. So you will always have it. Okay, so let's just plug in for what we know. We know from the given that the pressure of the gas is 250 kilopascals, but we know that we need homogeneous units. So let's go ahead and convert this so that we have that. Okay, this is our conversion. Conversion for units. Okay, times, what is the area of the piston? We just solved for it. You see how we're getting meters squared, meters squared? Okay. So here's our area of the piston. So now we need to deduct our atmospheric pressure, which is again going to be another conversion for units because this one was also given in kilopascals. So we've got 101 times same unit conversion. Okay. And again, conversion for units. Okay. And then we are going to multiply this by the area of the piston minus the area of the rod, which we just figured out those two things. So the area of the piston okay, and then we're going to deduct the mass of the piston, which is given. And then we're going to multiply that by the gravity constant. You will always have this. Okay. Because we assume things are on Earth. Okay, and then when we solve this, we get 933 newtons. Okay, so those are two examples regarding pressure. We're going to do a couple more, and we are going to do them with different systems. So we just used a piston. What we're going to go to now is a barometer and a manometer. These are two devices that are used to measure pressure. So we have a manometer, and it looks like this. If you remember from the lecture video, I went over how the pressure works a little bit in this. So this is how you'll actually use to solve it. I said we would do an example of it, and here we are. Okay. So this is the tank. This is the pressure of the gas. This right here is open to the atmosphere. Okay, and just a couple of things about a manometer. It is always open to the atmosphere. Okay, and here's some liquid right here. Okay, actually, let's pull this down a little bit. Okay, let's, well, whoa. Okay, yeah, more like that. Okay, so whoa, what is going on? What that was. Okay, so the manometer, liquid, we measure in terms of length of the column. Okay, so in terms of the length of the column, this is where we measure. So if it starts here and it rises up to here, we measure the length of the column. And this liquid can be mercury, you'll see mercury, or oil, etc. You'll see a few of them. Okay, let's see if I can make this a lot smaller. And so then we've got the barometer or barometer. And it looks like this. Okay. Then you've got this stack in the middle. Oops, sorry, I'm not very good at drawing straight lines. I promise they're not manufacturing this with that wave in the middle. Right here. Okay. We've got liquid, liquid, liquid. Okay. And this is not open to the atmosphere. Okay, and one fact about the barometer, which is different from the manometer, is it is never open to the atmosphere. Okay, and then this again can be this barometer liquid, can be mercury or oil, etc. Okay. So we've got 3 principles of a manometer or barometer, and I'm going to use a manometer just because I think it's easier to see kind of what these 3 principles mean. So we've got that. So let me just draw this again. Okay. Ugh, it's rough. Oh well, okay. Remember, we've got a tank. Okay, and so the first one is pressure at equal elevations. We kind of talked about this in the lecture. In a continuous mass of fluid, and that can be liquid or gas, at rest. So this is really important. It's only when this fluid is at rest and the whole system is at rest are equal. So if you remember, if we've got liquid right here, okay, and we have liquid right here, this right here, right? So we've got liquid, and all of this liquid. Okay, so this spot right here is equal, right? And so A and PA prime, these are equal because the system's at rest. Okay, so that's what this means right here. The second is pressure change across a fluid column of height. Oh, I don't even know what I was trying to spell there. That's rough. There it is. Height H is the change in P. Delta is change. There it is. Density, pH. And then, so this is the height. What does this mean? So that's this. This is our H. And it is the change in pressure from here to here. Okay. And then 3 is if a fluid at rest, very important, pressure increases as we move downward and decreases upward. So what does this mean? So sometimes you can have a manometer that has many more bends than just these two, right? So you can have it to where it's like this and like this. You know, you could have a couple of them. You could have more than this. And so a fluid at rest, so say you're, well, this really needs to come up here like this. Okay. So if you've got a fluid at rest, pressure increases as we move downward. So pressure is increasing as we move down, and then pressure decreases as we move up. So there's two things that I want to really note about this because it's really important for you to understand kind of how this pressure works. This is going to be a very critical part of the whole class. Is think of swimming, right? So when you are in really shallow water and you just dunk your head underwater, you can feel a little bit of the pressure of the water in your ears, but not too much, not super uncomfortable. There's not a ton at when you're very shallow when you're swimming. But what if you were to dive 50 meters down? The pressure would be a lot higher. You would feel that pressure on your body. You would feel it in your ears. And those, when you're a diver and you start from a shallow area and you dive deeper and deeper and deeper and deeper, that pressure is increasing because the weight of the water is on top of you. So that's how I want you to remember that as you go deeper or as you move downward, the pressure increases. And as you move upward, the pressure decreases. So that's the first thing that I want you to remember about this third principle. The next thing that I want you to remember is the direction of moving downward or moving upward. So if you remember for the first principle, these are equal, right? So this is equal, this is equal, this is equal, this is equal, right? So they're equal to, when it's at rest, pressure at equal elevations. This is equal to this, in a continuous mass of fluid at rest are equal. So when you're moving downward, if you think of yourself diving into this pipe and running through, going down, 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 and through is not the same thing as going downward. Going downward, we're talking about that y-axis. We're not talking about going through. So if you're right here and you're diving and you're diving and you're diving and you're diving and you're right here and you're diving and you're diving and you're diving and you're right here, you are not going to have any more weight of fluid on top of you to feel increased pressure than you would right here, because these are equal. But you will if you're right here versus right here. Okay, so if you start here and you dive to here, you will have an increased pressure because you're moving downward. But if you come into here and you're right here, this will have the same amount of pressure as this. And then if you continue diving and you swim all the way up to here, you will have less pressure than right here because you moved upward. So that's kind of how I want you to visualize how pressure works within this manometer. Okay, and let's do an example of a system at rest. And I'm just going to go ahead and get a new page because my pages they're having a little bit of trouble. Okay, so we've got an example of a system at rest. And what do we know right off the bat when we see system at rest? We know that pressure at equal elevations are the same. And we also know that force is pressure times area, because we've just done a couple of problems with that. We know that density, mass over volume, which is also equal to, so we can just rewrite it, okay? And then volume, denoted with a line across because we're going to be including velocity later, is area times length. This can also be height. So remember when we were looking at the manometer and we had the height of the column, that'll be your L. And then we've got change pressure equals density GH. Okay, so let's draw our schematic. Okay, down and up. I'm going to kind of try and draw it big for you guys so that you can really see. And they're usually not slanted like this too. It's just your wonderful example. Okay, so if we've got our fluid in here, and this is A, so this spot right here is A, and let's say that this is, so that's fluid 1 right here. Let's go ahead and denote our fluid 2. And this is a manometer. So let's go ahead and write down all of our knowns. This is fluid 2, which is mercury. Okay. And what do we know on a manometer at rest, or just a manometer in general. Right here it's open to the atmosphere, so we know that we have an atmospheric pressure pushing down. We know that a system at rest that points at equal elevation are equal. So right over here, this right here will be an equal pressure to A. So we'll just call this 1. And we'll call this B. And then we also know that our length or height is the difference between these two. And we know that, remember when I said, hey, if you start out diving, I mean, you obviously wouldn't be in a manometer, but if you can imagine yourself diving within the column of a manometer and you start right here and you dive downward, that the pressure increases. Well, then not only do you have this atmospheric pressure pushing down, but you also have the weight of this liquid right here, because as the pressure is pushing down, when you get to here, you have an increased pressure because all of this weight right here is on top of you. So you have the weight of this liquid, which is mercury. Okay, and so I can go in. There is a way that I can break down and show you how we derive this formula, but it's lengthy, so I'm going to skip that. But just let me know if that's something that you want to see, and I will show it. Okay, now that we know really what we're working with and we've put it into a schematic form, let's do another example that's going to give us some actual data to solve for. So what are we given? Water in the tank is pressurized and is measured by a multi-fluid manometer. So remember, we just had a manometer that had a fluid 1 and a fluid 2. So this is what we're given. H1 equals 0.1 meters. H2 equals 0.2 meters. H3 equals 0.35 meters. We've got row of oil equals 850 kilograms meter cubed. Row of mercury equals 13,600 kilograms meter cubed. And then we've got row of water equals, so we've got 3 fluids, 1,000 kilograms meter cubed. And then we've got atmospheric pressure, 85.6 kilopascals. Okay, and so let's draw our schematic. It will be given, but I find it helpful to always draw it live so that you can really see. Okay. Whoa. Okay. We'll just make that this. Okay. So we've got right here, we know that our manometer is open to atmospheric pressure. Now we've got water. And then we've got 0.1. This is air. Okay. And then, let's see. Okay. So right here is 0.2. Okay. And let's see. Right here is A. And right here is B. Okay. So let's plug in what we do know. So we know that our H1, here's 0.1, our height, because this is the same right here. This is our H1. Okay, we know that this is the same. B prime. Okay, and so this is our H2. Okay, and then we know that this is the same. This will be A prime. And this, oh no. Come on. Okay, this is H3. Okay, and so you can solve this either way that you want. If you want to start with 0.1 and then go through like this to solve it, or if you want to start on 0.2 and go down, you can do it from either way. I'm going to start from 0.2. I just like starting from here and going through, but you can do it either way. Neither is right neither is wrong. Both of them are right. Okay, and what do we need to find? We need to find the pressure of the air inside the tank. So pressure at 0.1 right here. That's what we need to find. So we're going to start with the given section. Because remember, we have those steps in the syllabus that was outlined. So first we start with the given section, which we did. Here's all of our givens. Then we state the find, which we did right here. And now we move to solution. Okay. And so I'll move right here, and I'm going to start at pressure 0.2. So P2 equals atmospheric pressure, right? Because if we're at 0.2, we're starting our little dive through the manometer. So if we're standing right here, we are at the point of the water. We're not under it, we are the point. So the only thing that is above us is the atmospheric pressure. So we've got PA equals PA prime, same fluid, same elevation. Oh, good Lord. I don't know what's going on, guys, but I'll try and figure this out after. Okay. And then PA prime equals PA equals P2 plus rho GH3. And we add this. We add because we are moving down. And pressure is increasing. Okay, So we have P2 is atmospheric pressure. PA, right here, if we're moving down, 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 because we need to find all of these points to find this. Moving down, and we need to know what PA prime is. Well, we know that PA prime is the same thing as PA, right? And so we know right here, PA equals P2, right here, plus rho GH of 3. Okay, because here's our height right here. Height of 3. Is that shown clearly enough for you guys? Let's see. 3. Okay, because we've got our formulas. So this is for point A. Well, this is point 2. This is A. And then we need to do B to get all of our points. So we've got atmospheric pressure, then we moved and solved for A. Now we're going to solve for B. So we've gotten this, we've dove down, we've gotten A prime, we've gotten A. Now let's get to B. We're right here, and this is the first time that we're moving up. So what do you think pressure is going to do? It's going to increase, that's right. Okay, so you've got pressure B is equal to what? B prime, right? So pressure B here, B prime is equal to pressure B. So if you're diving up to here, you're essentially diving up to here, right? Because it's the same pressure. We're concerned about pressure. Same fluid, same height. And then what does that mean? That means that what is the pressure at pressure B? Pressure at B, 1, or B prime, sorry. B prime equals pressure A, right here, minus, because we're going up, the pressure is increasing. Right here we added because we were going down, right? So now that we're coming back up, we need to deduct because the pressure is decreasing. So we need to deduct GH2. Okay, so let's kind of walk through what we have now. So we found out pressure at point 2, which is just the atmospheric pressure. We know that. Super easy. Okay. Then we need to get the one at point A. So point A is what's given. We know that from that we can find A prime. We did find A prime. What is the pressure at A prime at A? We know that the pressure at A prime and A is P2 right here plus this fluid right here. So rho GH3. This is the height. And then we need to get point B. So point B right here is the same thing as B prime. And what do we know from that? We know that right here when we've got pressure that it's point A minus, because we're going up, the density of oil, GH2, because this is our height. So it's the same formula, you're just working with separate points in the manometer. Okay, and so then we are going to look at point C, which is right here. Okay, point C, which is equal to P1 right here. And you're going down. So if you're starting from here and you're going down, you add just like here where you went down. So you're going down, you're going to add. This is water, the density of water. GH, which H are we looking for? This one right here. Okay. So now we've got points. Okay. Okay. So does that make sense? When you're moving down, you're going to add because the pressure is increasing. When you're going up, you're going to deduct because the pressure is decreasing. So you have done the pressure calculation formula writing for all the way to 0.1. So from 0.2 to 0.1. Okay. Now let's put them all together. So let me just erase this portion. We're almost done, guys. I promise my laptop won't die. Okay. So we've got P2 plus rho GH3 minus P oil GH. You're just combining them. Okay. And then we're going to move this to one side because what do we need to find? We need to find pressure at 0.1. So we're just going to move it around. Let's do that right here. Okay. You end up with but we need to have homogeneous units. So I'm going to do this kind of the long way so that you can see this work. Pascals over 1 kilopascals, 1,000 pascals, 1 kilopascals. And then we need to get this. Let's see, 1 Newton times meter squared. It's 1 Pascal plus, let's keep going. So that's our conversion. We're just plugging in. Cute. I'm trying to write slower so that my pen doesn't, it seems like when I start writing too fast that it starts to disconnect. Okay, and then I've got to drop down and come all the way over here. Okay, and when you calculate all of that, you get 647 pascals or 9.6 kilopascals. Okay, then we box in our answer. And this is where a lot of students make a lot of problems, is forgetting those unit conversions, but then you get really crazy numbers. Of course, work what you have. Partial credit is given, but really pay attention to those units. That way you start to understand kind of what looks like a normal answer so that you'll see, what red flags are, things like that. All right, so let's look at not another example. I just want to go over a couple of things, especially things that are going to be on your homework or on your test coming up. Again, we touched on the 0th law of thermo in the lecture, but I just want to highlight this is what's used to calibrate thermometers. And basically what that means is if you have, or if we consider A, B, and C, right? So these temperatures. So if temperature A equals temperature C and temperature B equals temperature C, then temperature A must equal temperature B. So that's what this whole thing means. Also on your homework, and I think on your test also, you're going to have temperature scales. Again, I did work a problem of this in the refresher, so I'm not going to work another one. But Kelvin is SI, and Rankine is EE. Our two major unit systems that we use are SI and EE. This is K. Rankine is R. And they have conversion factors. Factors are given. And when I mean conversion factors, I mean like temperature degrees, Rankine equals 1.8 Kelvin. Okay, so that's what I mean. Those are all given. A few definitions that I want you guys to know is, let's see, intensive properties versus extensive properties. So remember when I said, hey, remember intensive for independent, okay? Independent of size of system. And then this is dependent. It's just the opposite. So if you can remember this one, then you know this one. Dependent of size. Yep. And then what is some examples? Okay, so we've got pressure as an independent property, temp, density, specific volume, which is V, lowercase v. And then over here, we've got mass, volume, and energy. Okay. And then, so let's go over the systems. So remember, you've got 3 types of systems. Well, I really need these to be smaller. Okay. More like that. Okay. So if you've got these systems, and then you've got some sort of gas, liquid, things like that on the inside. Let's just say it's gas. You've got contents in here, and you've got a flame underneath each one. Okay, types of systems. Okay, so you've got what is called an open system. And this is when mass, let's draw the boundary so you guys can see. Ugh. Well, it's supposed to be boundary, guys. This is a lot harder than it looks. Okay, so on an open system, you have mass and mass, and it can transfer in and out, and then you've got heat, which is energy, and it can go in. So in an open system, mass and energy interaction with its surroundings. Right, so we see that. So if this is the boundary, mass can go in and out, and so can energy. When you have a closed system, we have no mass interaction. And energy interaction. Okay, so we've got heat, which is energy, and this can interact. Do you see it crossing the boundary? That means that it is interacting. But when we have mass on the inside and in these surroundings, it cannot interact. So do you see it's not crossing the barrier right here? It is not crossing. But right here it is, free for all. And right here it's going into. When you have an isolated system, remember we did talk about these. Remember we talked about these in the lecture. There is no mass and no energy interaction. Remember? So you've got heat, which is the energy, and it is going up, but there is no interaction across the boundary. You have mass. Whoa, okay. You have mass, it's going, mass, that is going, no interaction. So you have no mass, no energy interaction. And then we talked about boundary a little bit, so let's just go ahead and do a schematic of the parts and all the players. Okay. So right here. Okay, so if you've got a gas right here, you've got surroundings. Right? So this is the surroundings. And this is everything external to the system. And then you have the boundary, which can be, remember, can be real or imaginary. And it separates the system from the surroundings. And this can be fixed or moved. Okay, so I think that is it. I'll give you a definition of your system just while we're on here. And this is the subject of analysis. And so in this example, you would have gas as your subject of analysis. And then you would have a boundary if this is a piston, which is drawn as a piston. Then your boundary would be the piston walls. And then your surroundings would be everything external to it. If you're standing outside of the piston, you would be part of the surroundings, the everything external. Okay, so this should help you immensely on your homework and of course on your upcoming test. Let me know if you have any questions.